Swayam Prabha. Digital India. Educated India.
Today we are going to talk about some of the composite materials with a special focus on the fibers of some of these composite materials. So we are going to talk about fiber reinforced composites and mostly polymer matrix composites. That's the first very important thing. Then also we will talk about little bit on metal matrix and ceramic matrix composite. Now when I am talking about polymer matrix composite, what we are telling is that the matrix has to be polymer, okay. But what about the reinforcement? We are remaining silent about it, but the reinforcements for polymer matrix composites are generally either polymer or ceramic. When we are talking about metal matrix composite, then so these are the reinforcements. Then it will be either metal itself as a metallic fiber or ceramics. The reason why polymer and ceramics for polymer matrix composites are chosen because of one is the matching of coefficient of thermal expansion plays an important role, and secondly the strength and exactly the interlocking that takes place between the fiber and the matrix, that plays an important role. So also in the fabrication process plays an important role. So this is metal matrix, and for ceramic matrix composite it is the same thing, metal or ceramics. For carbon-carbon composites, carbon itself is the matrix and carbon itself is the reinforcement, okay, mostly in a carbon or graphite form. So this is what we are going to have an overview on the whole thing, and then finally we are going to talk about structural composites. That means how do you make a composite layer by layer. Now let's first talk about fiber reinforced composites. So the first example of such composites is GFRP, that is glass fiber reinforced composites, and that name itself is telling us that the reinforcement is glass fiber. And when we talk about glass fiber, there are various types of glass fibers. There are in fact something like E-glass fiber, that is for electrical purposes, insulations, that was first discovered. So it is important. Then there are now couple of very specific glass fibers like S-glass fiber, which is good from strength point of view. So this is available today as a special type, and also C-glass fiber. So this is against corrosion, from the corrosion point of view. So however, the most common one is actually E-glass fiber, and the most common matrix is actually epoxy polyester resins. The diameter of this fiber is between 3 to 20 micron meter. And typically in each one of these fiber, if you look at the composition, you will see about 55% silica. So silica has the major composition, then 16% calcium oxide, 15% alumina, 10% boron oxide, and 4% magnesium oxide. So all these things together actually makes the glass fiber. In fact, you can see the glass fiber here. You can see it here, that this the first one and the second one, these are the two where the fibers are actually whitish, transparent or translucent in nature. These are the glass fibers. So this is the simple fiber, and this is the fiber when it is having some crosses in it to keep it in two positions. So these are the two glass fiber examples. So these are the glass fibers, and then if I actually apply the epoxy resin, then it becomes a composite, and this composite will look something like this. So you can see that the fibers are there inside, and then there are layers of these epoxy resins, the polymeric resins that are applied, and finally you get a strong structural composite out of the whole system. Of course, there is also one embedded damage in it, rectangular damage. I will talk about such a thing at a later stage, but this is an example of a glass fiber reinforced composite. So, what is the kind of weightage possible? By weightage, what do you mean? What is the maximum fiber volume fraction possible? That is generally 0.6. That means 60% volume will be fiber maximum. You try to always increase the amount of fiber in order to improve the strength, modulus of elasticity, etc. So 60% is generally the maximum possible, and 40% then is the epoxy matrix. With that composition, the density will come about 2100 kg per meter cube. Just compare that with the density of steel, and that is about 7400 kg per meter cube. So you can see that how light this system is. The tensile modulus is about 45 gigapascal. Just compare this with something very close will be maybe aluminum, which is close to 70 gigapascal. And this is, however, an isotropic. This is the longitudinal modulus, and the transverse modulus is much lower, that is 12. If you remember the spring analogy that I have shown in the last class, that explains this. Then the tensile strength is about 1020 MPa for the longitudinal direction and about 40 MPa in the transverse direction. The only limitation, so structurally it is quite good. In fact, wherever steel with moderately loaded element is needed, or aluminum, you can very safely use today the glass fiber reinforced plastic. If you need slightly more strength, you can go for S glasses, etc. But the limitation is that the surface temperature is up to 200 degrees centigrade. It should not go beyond that. If it goes, then the flow will start, or the degradation of the matrix will start. So hence, this is the limitation, the temperature wise. There are many applications of it, like you can see automotive and marine bodies. Many of the sports yachts, for example, are actually made of glass fiber reinforced plastics, because that way you can make it very light. And then the plastic pipes, storage containers, industrial floorings, you can see that this is a typical bar, ribbed bar, which is made of actually GFRP rebars, which is used for making the pedestrian bridges. So there are varied applications, and GFRP is coming up to be one of the most I would say widely used composite for because of these advantages. The next composite, which has very high performance applications, are actually carbon fiber reinforced polymer composites. So carbon fiber, if you look at it, once again I will show you how it looks like. These blackish things, these are the carbon fibers, and in various forms you can have. This is unidirectional fiber, and then you can have such carbon fibers which are in an oven form, for example, okay, or in cross plies or prepreg forms, okay, random orientations, etc. You can have it, the carbon fibers in various forms. So these three, 1, 2, 3, these are the examples of carbon fibers. So you can, just like GFRP, you can actually make carbon fiber reinforced composites. Now, carbon is a very high performance fiber in comparison to glass fiber. It has very high specific modulus, E/ρ ratio, that is modulus of elasticity to density ratio, and also it has a very high specific strength. So high specific modulus and high specific strength. Not only that, it can retain the same at elevated temperature. GFRP by 200 degrees centigrade, it is of no use, whereas CFRP can be used to a much higher degree of temperature. And at room temperature, it is not affected by moisture or a wide variety of solvents, acids and bases, but the manufacturing process is relatively inexpensive and cost effective. It is expensive, particularly the carbon fibers are expensive. So with the same 0.6 kind of a volume fraction, and the fiber diameter about 4 to 10 micron meter, you will achieve here a density of 1600. That means C carbon fiber is actually lighter in terms of density. The rho, the density of the carbon fiber, okay, that is lighter than the density of the glass fiber. So that is something that is very important. On the other hand, if you look at the tensile modulus, you get something like 145, which is very close to steel, double the aluminum. Transverse highly anisotropic, transverse is only 10 GPa, and tensile strength is 1240 MPa, transverse strength is about 40 MPa. So that is, this anisotropy is something that one has to keep in mind while making a structural composite out of this system. These are various applications of carbon fiber composites. As you can see that this is a BMW carbon fiber wheel. Okay, this is the steering of carbon fiber. Okay, this is the steering of carbon fiber, and then there is the special seats, etc. So there are many applications of carbon fiber. You will see bikes, for example, mountain bike frames. You will see 787 Dreamliner has nearly 50% frame made of CFRP. And the other interesting application is in terms of the racing cars like Lamborghini Aventador. You will see that CFRP is used in its wheels, in its frames, and in the seats itself. CFRP is used. CFRP is also getting lot of use in the sports goods, for example the rackets. So by making it light but strong, you can actually save lot of muscular energy, and hence you can improve the performance in a game. So thus CFRP is very well popular in such sports applications as well. The third one in the polymer matrix composite that is equally important in terms of application is actually aramid fiber reinforced polymer, AFRP. So here the fiber is like last two are the glass fiber and carbon fiber, but in this case the fiber is actually polyaramid fiber. Once again I will show you how would it look like. So this one, these yellowish ones, these are the polyaramid fibers. You can get it in various forms as simple fibers as well as woven fibers, so woven cloths, bidirectionals. So these are actually Kevlar, or Nomex, that is the name of such a system. So this actually is very much known for its toughness, impact resistance, resistance to creep and fatigue failure, and the reason of its high strength is because of the axial covalent bonds, and however it is very anisotropic. It has weak hydrogen bond in the transverse direction, and it has negative coefficient of expansion due to kinks. So that is also another interesting point you have to keep in mind while designing, and it is UV sensitive. That is a little bit of a negative side of it, that it degrades in the UV exposure. Now Kevlar with a 0.6 volume fraction, you can see that the density is only 1440, so it is even lighter than CFRP in some of the cases, and definitely it is lighter than GFRP. And if you look at the tensile modulus, close to aluminum, 76 GPa in the longitudinal, transverse it is pretty weak, only 5.5, and this is tensile modulus. The tensile strength is 1380 MPa in the longitudinal direction and 30 MPa in the transverse direction. One important thing we have to keep in our mind that in terms of fibers, glass fiber is inorganic in nature. Carbon fiber, well, you may call carbon inorganic or organic, but definitely this one, the aramid based fiber, this has the organic fiber. That organic fiber is actually this polyparaphenylene, terephthalate or similar such fibers. So that is about the Kevlar fiber. Typical applications, one of the most important application today is for the BPJs or in other words the bulletproof jackets or vests. So it is because of its lightweight but high shock absorption capability, it is used in ballistic products. Also it is used in sports goods, ropes for the climbers and missile cases, and in many cases it is working nicely as a replacement of asbestos in automatic brake and clutch linings. See, asbestos is a good fiber, but the problem of asbestos is that it is injurious to the health. So in such cases this particular fiber is actually working very well as a replacement. Now if we compare between the three types of composites with the same volume fraction 0.6 and the same matrix, epoxy matrix, otherwise it will not be a fair comparison. GFRP density is the highest, 2100. Polyaramides, they are in the middle, 1440. In fact they are the lightest, and CFRP is 1600. So you can call polyaramide to be the lightest and GFRP to be the heaviest among them. And if you look at it from the stiffness point of view, then CFRP is very stiff. So this is very high stiffness. So very high stiffness. In fact, close to steel, somewhat more than steel in the longitudinal direction. In the transverse it is only 10, and the tensile strength wise it is close to steel, that is 1240 megapascal, whereas transverse it is about 40. So in many sense, other than the density, CFRP is better because it has higher modulus of elasticity and higher strength in comparison to the other two materials which are mostly used. Now I will talk about the metal matrix composites. So in the metal matrix composite, the fiber can be either metal or ceramics. But polymers typically we do not keep because they cannot sustain a high temperature, and also there are this mismatch of coefficient of thermal expansion and also the conductivities, etc. So matrix wise here it is ductile metal, usually it is alloys of aluminum, magnesium, titanium and copper, and fiber wise it can be carbon fiber, silicon carbide, so these are inorganic fibers, then boron fiber and aluminum oxide, that is a ceramic fiber. Any one of these fibers can be used in the metal matrix composite. Advantage over PMC is definitely high operating temperature and definitely non-flammability and greater resistance to degradation by organic fluid. In many chemical plants there is this organic fluids which can contaminate the pipelines. So this MMC is much better in all such cases, including a good operating temperature. So in fact some of the MMCs, if you look at it, like carbon and aluminum as matrix, you can see you can get a very high tensile modulus, something like 320, and the strength is something like 620. So this is very high considering the density is only 2.44. Similarly, if you look at all of them, you will get a kind of an idea that where exactly we are in terms of the metal matrix composites, and in most all the cases it is much better than the single metal based system. The places where you can use it, like golf definitely, and then the tubular struts which is used as the frame and rib truss members in the fuselage section, that is in terms of aircraft applications. Then the antenna boom for Hubble Space Telescopes for space application, or tank armor, MMC. So there are many such varied applications of metal matrix composites. Now we will talk about the ceramic matrix composite. Now ceramics are highly brittle in nature, we know that, right? And it has low fracture toughness. So you have to handle them very carefully. That's the first important thing. In fact, to handle the ceramic fibers, we do something which is known as actually sizing. Sizing means you take a ceramic fiber and then you apply a oil coating over it. okay, and what coating you are giving, that is a trade secret, because that enhances the life of the fibers and that increases the fracture toughness. Now in general the fracture toughness of ceramics is only about 1 to 5 MPa square root meter, and for metal it is only about 20 to 90 MPa square root meter. So when you will be using CMC, then your target will be to lie, as far as the fracture toughness is concerned, in the area of 6 to 20 megapascal root meter. Now the crack initiation normally occurs here within the matrix space, whereas crack propagation is generally hindered by the particles, fibers or whiskers, whatever you have inside in the matrix, that will actually sort of stop the growth of the crack, and it exhibit improved high temperature creep behavior and resistance to thermal shock. So these are some of the very good characteristics of ceramic matrix composites. There is one interesting ceramic matrix, I don't know whether we will call it composites or not, but cermet. So cermet is actually a composite of ceramic particles which are very strong and brittle, and that is kept in a metal matrix like soft and ductile metal matrix. It has higher stiffness, toughness and wear resistance than the traditional materials. For instance, tungsten carbide or titanium carbide ceramics embedded in a matrix of a metal such as cobalt or nickel. That is one of the examples, and it is only about 10 to 15% of the metal volume, and it is used for cutting tools because you get a very good hardness out of it, okay, and the electrical components also it has used, such as in resistors or vacuum tubes, etc. So here are some examples, as you can see, of cermet trimming potentiometer, cermet inserts, etc. So that is about ceramic plus metal together producing something called cermet. Next is the carbon-carbon composites, where the carbon is the fiber and carbon is the matrix. So here it's very expensive because the procedure by which we do it is also very expensive. It has a high modulus of elasticity to up to 200 GPa and strength, and it can retain its property even up to 2000 degrees centigrade, which is a very high temperature. Also it has a low density, high thermal conductivity, it has a low coefficient of friction, and it has high abrasion resistance. That is why it is used in missile cones, in B-2 bombers, in wing leading edges of the space shuttle. So wherever there is a very challenging environment, we actually apply these carbon-carbon composites. Now finally, I will talk about the structural composites, which means how do you make them layer by layer. So yesterday in the last class itself, I have explained you that a laminate is constructed by stacking a number of laminae. Examples are unidirectional laminate, for example, where the fiber orientation angle is the same in all lamina, such as 0 degree, or the cross ply laminates where it is like 0, 90, 0, 90. If you want to put any other arbitrary angle of the fiber, then we will call it angle ply laminate, which is like theta minus theta, theta minus theta, etc. And more importantly, you can stack them in such a way that with respect to the mid plane, they can be either symmetric or they can be unsymmetric. So there are many variations that you can develop, and each has its own characteristics. Now if you consider a symmetric laminate, so if there is a bar over such a sequence like 0, 45, 90 bar, then that would mean that that's the plane of symmetry passes the midway through the thickness of this particular line. And the adjacent, if you have plus 45 minus 45, you can also put it as plus minus 45. For adjacent 0 degree plies, if you get whatever numbers are adjacent, you can put them as 0, 4. and two adjacent plus minus 45s are grouped, you can put them as plus minus 45 2. So that's, you can actually use these code names in order to make a symmetric laminate. Similarly, antisymmetric also, suppose there are 4 layers, you can put it in this manner, okay, or antisymmetric, another is plus theta minus theta plus theta minus theta. That means for every plus theta, the next layer is actually minus theta. There is another one which is known as quasi-isotropic laminate. Quasi means it is only isotropic under certain special cases. For example, if you consider that a composite which has ply angles only at the ratio of pi over n, suppose if it is 3 layers, then it is 60-degree ratio, 0 plus 60 minus 60. Similarly, with 4n as 4, it is 4 layer ratio. So this is known as quasi-isotropic. The reason is that if the stiffness matrix, it is found out for such material, the in-plane stiffness does not vary with the direction. So that's the telltale sign of isotropic situation, where the properties do not vary with the direction. In this case it happens, but only for the in-plane properties. That's why it is called quasi-isotropic, not fully isotropic. The other structural variation is known as sandwich panels. It consists of two strong and stiff sheet faces that are separated by a core material or structure. Usually the core material is a honeycomb structure. They try to reduce the weight this way, and it has an outer sheet which has aluminum alloys, fiber reinforced plastic, titanium, steel or plywood. And the core material is actually rigid polymeric foams, example phenolics, epoxy, polyurethane, and then wood and honeycomb. So it's one of the lightest material and technology in terms of the composite material. Sandwich panels are used in various applications like low water absorption, good anti-corrosion activities, and good thermally insulated capacity. So it is very popular in terms of its use. Finally, there is this hybrid composites where it's very rare, it's mostly in the lab scale, but generally for a very demanding thing you may have to design it. Two or more different kinds of fibers will appear in a single matrix. For example, using carbon fibers, there is a strong and relatively stiff, and it provides low density reinforcement, but it is expensive. Now suppose I add glass fiber, which is inexpensive but lack the stiffness of carbon, then the two together will possibly make the stiffness to be little better and the cost you need to be little better. So that's how it can solve some of the contradictions. The glass carbon hybrid is stronger and tougher, and it has a higher impact resistance. Now the fibers may be aligned or intermittently mixed with one another, or laminate can be constructed. So it can be something like, as you can see, that 3 layers are only given, or the 6 layers will be also given, so that you can prepare various types of such composites. So this is where we will close, and in the next lecture we will learn about manufacturing and processing of composites. Thank you.